we go. Okay. So he did his undergraduate at that fine upstanding school up the street, University of Waterloo. He graduated from there. We have a lot of Waterloo graduates here as well. And went down to California, did your graduate work, was Caltech, and your postdoc was Berkeley?
No, actually, straight to Davis after my.
Straight to Davis, yeah. Okay. Went there, and you've been teaching at Davis since 1993. I got that right?
1999.
1999. I'm just making stuff up. So we've known each other for quite some time. We've shared interest in air pollution and ultrafine particles. I've often thought of Mike's work more in terms of the modeling, but now there's a lot of measurements as well, and I think he's really bringing those together. So you've got measurements and modeling ultrafine particles. 15 years. You're accusing me of making you feel old, but we'll go with that. So I'll ask you to join me in welcoming Mike Kleeman.
Thank you, and thank you for the invitation to come. We've been trying to set this up for quite a few years. I travel to Ontario to see my family regularly, but it always seems that time is never in excess when I do that. So I've never actually forced a trip to come here and speak. So this is a dedicated trip in combination with a defense to come and see you guys. A lot of what I'll talk about today is going to be evidence over many years. So I'm going to try to summarize whole papers with one slide, which oftentimes doesn't do it justice, but I'm trying to paint the picture, I guess, at that high-level scale over many years. And I'll rely not just on my own data that I've made measurements of over those years, but also collaborators, Kostas Iotis. So this was a talk that I originally put together with Kostas to present at the EPA workshop on ultrafine particles, which we had last year. And so I wanted to try to revisit that because I thought it painted a really nice picture, and I thought it might be of interest to this audience as well. So I'll talk a little bit about the different metrics that we use for ultrafine particles. I apologize to those sitting there. I was instructed to stand by the microphone, so I'm blocking your view, so I apologize. I'll try to move around a little bit so you get a view of the screen every once in a while. So what do we mean by ultrafine particles? And there's still some discussion about what we should use to characterize them when we try to do health effects analysis, and I'll try to address that topic. And then talk about the sources of ultrafine particles, how they transform in the atmosphere, and then the tools that we use to understand which sources are important and how to do exposure assessment, ultimately trying to build a picture both with toxicology and epidemiology, because you need both if you want to regulate something. So it's not enough to be able to say that something is toxic in an inhalation exposure chamber. You have to have epidemiology, and it's not enough to have epidemiology to drive a new standard. You need the toxicology as well. You need the picture that spans the whole spectrum, and I think that evidence emerges in this talk, but it'll be interesting to see if other researchers are able to confirm this in the future and where that takes us as a community. So we'll start out with ultrafine particle metrics then. And most of you that do ultrafine work, it's synonymous now with number concentration. And the idea being then that the ultrafine particles are those particles smaller than 100 nanometers, and that's the portion of the airborne particle size distribution that's usually not a lot of mass in there. There's typically only 1 to 5 micrograms per cubic meter of mass, where there may be 50 or even 100 micrograms per cubic meter in the whole size distribution. But most of the number distribution is in that size range. And the off-the-shelf instruments that are available for making ultrafine particle measurements count particle number very efficiently. And so there's been a lot of work that's been done with particle number now, sort of as a synonym almost for what ultrafine particles are. But really the interest in the ultrafine particle size fraction didn't start out with number, it started out with surface area. And the hypothesis was that the surface area is where all the chemistry will happen, and if you expose yourself to a lot of surface area particles, you're getting a lot of chemical reactions. That might be what drives the health effects. And it turns out that number is better than PM2.5. It's more correlated with surface area than PM2.5 is, but it's not perfectly correlated. And there are other metrics that you could look at. One of them that I'll try to justify today is the PM0.1 mass, the mass of particles that have aerodynamic diameter smaller than 100 nanometers, basically. So PM2.5, now I'm talking PM0.1. And it turns out that mode of that fraction of the size distribution lines up even better with surface area particles than number does. So if I take data from Fresno, California, which is where these measurements were made, and I look at the surface area of the particles here on the lower axis, and I try to see what correlates with that, I can either do it with particle number here on the left or particle mass here. Those correspond to the blue lines or the red lines. And what I observe is that particle number is correlated with the surface area with an R squared of around 0.7. But if I look at PM 0.1 and how that's correlated with surface area, it's 0.97. So it actually is a legitimate metric to look at for the surface area of particles. And it turns out that it has a number of advantages compared to the number. And I'll try to go into those as we go forward. So ultrafine particles, there's a lot of dynamic stuff happening in that range. They're emitted from all combustion sources. And so you can get them being emitted from your cars, from your barbecues, from anything that's burning a fuel is going to emit ultrafine particles. You can also be nucleating them in the atmosphere straight up. And so the process of spontaneous formation of new particles in the atmosphere generates ultrafine particles that then grow up into the accumulation. There's then this period, if you're generating it from a source, which is most of what I'll focus on today, you get this atmospheric dilution effect, and a lot of dynamic things happen there. These particles can evaporate, they can condense, they can be changing their sizes very quickly, and a lot of that plays out in the number concentration very strongly. So I'll show in a slide or two this very strong evaporation effect downwind of roadways of particle number, which is very difficult to then characterize exposure classification based on that number metric because it's changing so rapidly. So many dynamic things are happening. And we don't have perfect ability to predict that either. It's very difficult to predict that in a way that you could imagine applying over Toronto, for example, at fine spatial scales. And so that's tough. And then you've also got this atmospheric aging and photochemical reaction that goes on. And Costas has made a lot of measurements in Southern California showing how as things are aging in the atmosphere, they perhaps become more toxic. And so we have this very dynamic system, and we have to think about how number or perhaps the PM 0.1 metric has advantages and disadvantages in this context. So let's start out then looking at our first stage of the life of the ultrafine particle in the emission stage. So this, I'm talking about seconds after release. In a typical emissions test that we would do, we would average for maybe 60 seconds to characterize the near source emissions of those particles. One of the big results that's come out of California in the past decade has been this realization that you have these very high number concentrations of particles adjacent to roadways, and if you move downwind of the roadway, they appear to evaporate. That means that if you look at their concentration relative to the carbon monoxide, which is a sort of a stable tracer for the roadside emissions, then the number concentration drops off faster than the carbon monoxide concentration. So we expect dilution downwind of roadways, but we get more than that. We get actual evaporation of those very small particles. So you can look at that two ways. If you live more than 300 meters away from a roadway, that's awesome for you, and you're not getting exposed to this high concentration of particles. Or if you're near the roadway, more than 300 meters, or closer than 300 meters, that's terrible for you because you're getting exposed to a very high concentration of this. Does that have a health effect or not? Well, we'll talk about toxicology in a bit, but California thought this was important enough that there is now a law that you cannot place a school closer than 300 meters to a roadway because of this type of effect. And so this was one of the results that's come out of research in California due to Costas's work. He was involved in that study. Now, PM 0.1 is much more stable than that. When we measure them on a dynamometer, that metric, you can get reproducible concentrations. When we measure them in the roadside, they don't evaporate as quickly as the number concentration does. And that's because of where those particle numbers are. Those very, very high concentrations of particle numbers are showing up in the size distribution at 20 to 30 to 40 nanometers in size. And that, there's not a lot of particle mass there. If you want to look at where the PM 0.1 comes from, it's the tail of the PM 2.5 size distribution that dips below 100 nanometers. And so most of the PM 0.1 mass is dominated by particles from 56 nanometers to 100 nanometers, whereas most of the number is smaller than 56 nanometers. And that's why you get this apparent contradiction, where one of those metrics of ultrafine particles is very dynamic, the number, and one of them is more stable. And so we think that the PM 0.1 is much more stable, and for that reason, you can do a better job of exposure characterization to PM 0.1 than you can to number, which makes epidemiology possible, as I'll try to get to in this talk. So these are driving cycles. This is the federal test procedure cycle, by and large, for different types of motor vehicles. And the driving cycle is in the dash line here. So you can see that when you have hard accelerations, especially when the vehicle is cold, all these were cold starts, that you get very high emissions of these PM 0.1. And then in certain periods of hard acceleration, again, you can get higher emissions. And then you see much, much lower emissions. So lots of things going on with the drive cycle of the car. But again, it's better than looking at numbers. So we know also that number and mass can go in different directions depending on the vehicle technology that's being applied. And so we've learned then that as we control the mass of particles being emitted from, say, a diesel vehicle by installing a diesel particle filter on that vehicle, that you could certainly get a 90 or 95% reduction in the PM 2.5 emissions from that vehicle. But sort of conversely, the number emissions go up. Again, because you're getting a lot of these very, very small particles in the 20 to 40 nanometer size range that are then being counted as individual particles. And so there's some concern then that as we adopt these new technologies that will improve on the mass emissions rate, but will be actually getting worse on the number emissions factor for certain technologies. And so this is just a plot for heavy-duty diesel vehicles showing number emissions versus mass emissions, two vehicles in a baseline measurement, and then as you apply the diesel particle filters, watching how the mass comes down, but the number actually goes up. And again, that's due to nucleation of semi-volatile particles. So if you were to heat these up in the thermometer to do the official regulatory measurement, a lot of these things would go away, which probably means that they probably also evaporate downwind of the roadway because they're semi-volatile. So just something to be aware of as we go through it. Now, we've built up a large number of measurements of gasoline vehicles and diesel vehicles looking at the particle size distribution and the chemical composition. So these are plots from individual light-duty gasoline vehicle tests, light-duty gasoline vehicle 1, driving on the federal test procedure cycle. This is particle diameter on the lower axis, and then the mass of the particles on the vertical axis. The solid material is the elemental carbon, sort of the very non-volatile carbon, and the hatch material is the organic compounds, which encompass hundreds, if not thousands, of different individual organic compounds, and all sort of smashed together on that. And what we see then is this dipping down of the mode below 100 nanometers. That's the PM 0.1 tail that I'm talking about. But then this is also, you know, highly correlated with the PM 2.5 mass. And so we expect to some degree that technologies that would change the PM 2.5 mass will also change the PM 0.1 mass. And so to some degree, those hypotheses are linked. Perhaps the PM 2.5 effect that we see is actually the PM 0.1 effect. And I'll try to come back to that as we go forward. So if we look then at how the PM 2.5 concentrations have changed in Los Angeles as we adopt new technology, as we adopt these diesel particle filters, what you can see then is that as we go from 2002 to 2006 before diesel particle filters to 2008 to 2012 after diesel particle filters, we're seeing a 20 to 30% reduction in the contribution of traffic to PM 2.5 because of that change. That will have a PM 0.1 effect. It wasn't quantified, it wasn't necessarily widely monitored as it happened, but that technology did lower PM 0.1 the same way that it lowered PM 2.5. So these are measurements at Central Los Angeles, and then at Rubidoux and Riverside. This is sort of in the middle of the emissions, of the fresh emissions, and then this is downwind after it's aged for a day or so and had more time for chemical reaction. Now, we also know that there's pretty sharp spatial gradients for the PM 0.1, and that comes out in the PM 0.1 mass, but then also if you want to look at any of the chemical components that make up PM 0.1. So this particular measurement data set was done for metals, looking at all of them here. You've got things that are sort of crustal type metals, and then things that are more traditionally dominated by motor vehicles. So copper and barium in this case, a lot of that in brake wear, and there is some brake wear that dips down into the PM 0.1 mode, as well as being sort of a coarse particle. And these are all ratios then of a measurement made at Wilshire or 710 or 110, sort of around freeways, versus the measurements that were made at an urban background site. And so where you see the number being much greater than 1, you know that you're getting much, much higher concentrations than what's over the urban background. And you can see that there's significant enhancements of the ultrafine particles, and for especially the things that are associated with traffic, like the brake wear, as you go to some of these sites. So, and that'll be a theme that comes out as well, which also makes it difficult to do population exposure estimates, is that there's really sharp spatial gradients for PM 0.1, or certainly number as well. And that means that it's very difficult to use central site monitors the same way that we've used them for PM 2.5. PM 2.5, we got away with doing central site monitor estimations because the PM 2.5 gradients aren't that sharp. And so what we measure in the middle of Toronto somewhat correlates to what you're breathing here. Whereas the ultrafine particle spatial gradients are much sharper. And unless we're going to invest heavily in a measurement network, we're going to have a hard time measuring our way into doing a realistic exposure estimate with ultrafine particles. And that's part of the complexity of those. Just a quick note, Costas Siotis, he does a lot of his measurements with the Siotis impactor, which actually isn't strictly speaking PM 0.1, it's more like PM 0.25, but again, we think that those things are cousins, if not directly related to each other. And so I'm using a lot of his data here as if it was PM 0.1. It's a slightly larger size fraction. Same sort of discussion now with PAHs instead of the metals. And so again, you can see a very strong difference in terms of the urban background signal in the light blue here versus the heavy traffic dominated signal for these ultrafine particle PAHs now, pyrene, benzo-GHI, fluoranthene, and so on. These are all the lighter ones, and then through to the heavier ones as well. That just means low molecular weight and high molecular weight. The low molecular weight ones tend to be in the gas phase and the particle phase. The heavy molecular weight ones tend to be only in the particle phase. And so you can see that sort of behavior sort of across the spectrum of PAHs that you might be interested in. And PAHs are often, linked with various toxicology outcomes. And so we think that they're drivers of health effects as well. They're in ultrafine particles, sharp spatial gradients again. Here, Costas was just trying to convert that PAH estimate into a cancer risk to try to make it real for people. And so looking at the difference in the pH exposure from ultrafine particles in the subway or light rail versus freeways and surface streets. So should you be taking public transit, the subway and light rail, Los Angeles actually has some of that, believe it or not, or should you be driving your car? And the take-home message is that you'll have a far lower cancer risk due to exposure to ultrafine particles and pHs if you were off the road, basically, not driving in your car. So traffic is a dominant signal for these things. Okay, so that's all fresh emissions. Talk a little bit about atmospheric dilution and photochemical aging now. So Costas lives in Los Angeles, where there's obviously a mega city with a lot of opportunity to do studies of this sort. And so he's done a lot of characterization here in central Los Angeles, around the USC campus, looking at the fresh emissions, and then comparing that to what he sees out at Riverside, where you have the opportunity for photochemical aging. The dominant wind direction is onshore, so you typically move things from the upwind areas of the air basin to the downwind areas of the air basin in something like 1 to 3 days. You can't really hold the air in Los Angeles for longer than that, typically. And then we've also got the port situation happening here as well. And so again, this was a study where the Siotis impactor was deployed, and we were looking then, Costas was looking at the upwind, downwind differences, the seasonal differences, and even the time of day differences, just trying to draw contrasts in how the ultrafine particles and the particle mixture is changing at those different locations and times. So here we're doing a comparison of summer on the left versus winter trends. These are sites then from the left to the right, moving from upwind to inland in both of those plots. And we're looking at elemental carbon, the water-insoluble organic compounds, the water-soluble organic compounds due to, I think, biomass burning, and then the non-biomass burning fraction of the water-soluble organic compounds in the different colors here. And what you tend to see then is that in the wintertime, the ultrafine particle concentrations tend to be higher in the source regions where it's being generated. That's sort of more towards central Los Angeles. But in the summertime, what you tend to see is that you get higher concentrations of these ultrafine particles at the downwind receptor sites. And so Costas argues then that that's evidence of photochemical transformation of those ultrafine particles, where they're chemically reacting. Things are either changing them directly in the particle phase, or you're getting new material that's forming in the particle phase as we go from upwind to downwind. And so especially we're seeing higher concentrations of water-soluble polar organic compounds as you go downwind in the summertime. So the photochemical aging looks like it's producing some more of this water-soluble organic material in the ultrafine size fraction, the PM 0.25. So the ultrafine particle metals are also more water-soluble in the than the coarse particle metals. And that kind of makes sense intuitively. The coarse particle metals are crustal material largely, and they're oxidized, and they're sort of tied up. They're not necessarily going to dissolve in solution. If you throw a rock into solution, it doesn't necessarily immediately dissolve. Whereas if you would take that rock and burn it, essentially, and renucleate it as a new, 20, 40, 50 nanometer particle, that material is not nearly as oxidized and is not nearly as tied up in a geological form. It's much more available to go into solution. That has implications. So if we walk around outside and kick up some dirt and you breathe it, those metals, by and large, aren't going to cross cell membranes because they're too big in the particles that they're in, and they're not going to dissolve in your body fluids. Whereas if we sit there and heat it up to the point where you get it to flash into the vapor phase and then come back as an ultrafine particle, it will cross your cell membranes and it will be dissolvable in your bodily fluids, and it can go lots of interesting different places in your body. That's essentially what happens out on the freeways. Your tires are kicking up road dust all the time. That road dust, some of it gets sucked into the combustion intake of your car, and it's coming out the tailpipe as ultrafine metals. And so you're breathing this. If you're in Toronto, you're breathing this all day, every day. So it's a real effect, and it matters then that these things are more water soluble. Okay, so we've invested a lot in trying to do source apportionment of ultrafine particles with this PM 0.1. And so we made a lot of measurements of the sources of ultrafine particles. Heavy-duty vehicles shown here, but light-duty vehicles, food cooking, all the different major sources, and trying to segregate it by particle size so that we're interested in this last bar, the ultrafine particle size fraction. One of the interesting insights that came out of this is that really motor oil and some other organic carbon that comes out of motor vehicles are separate in distinct size distributions, and they can do their own separate things, basically. And so that was a good realization to be able to do the source apportionment, where if we would have just blindly applied the PM 2.5 source profiles to the ultrafine particles, we would have really been confused and got the wrong answer if we would have tried to do the source apportionment of the PM 0.1. So when we do those types of studies downwind of roadways, we see more or less what we expect. So these are measurements made upwind and downwind of a freeway, and I've sort of background subtracted the upwind. So I'm looking at 18 meters downwind of a freeway or 37 meters downwind of a freeway. This was in San Diego by Kim Prather's lab by UC San Diego. This is particle diameter, again, on the lower axis, and then the particle mass on the vertical axis. Again, the dark shading is one of the chemical compounds. We're looking now source apportionment, so that's motor oil, and then diesel fuel, and then gasoline fuel, and then unknown in the open bars. And what we see is that the ultrafine particles that dip below 100 nanometers, 0.1 microns, we can explain a lot of that material. So this is for elemental carbon here in the left panels, or organic compounds here in the right panels. We can explain most of that material, and it makes sense. What we can't explain is this accumulation mode material that grows in sort of above 100 nanometers. And we think that that's secondary organic aerosol or processed primary organic aerosol that's been transformed. But the ultrafine particle signal is much cleaner. It looks much more like fresh source emissions. That also makes your life easier if you want to do population exposure estimates, where there's not, I think, a lot of transformation of those ultrafine particles. They more reflect fresh sources than, say, a PM 2.5 measurement does, where there's a lot of atmospheric processing that could go into that. And so that is one of the things that's working in our favor, we think, when we work with PM 0.1 as opposed to PM 2.5, one of the few things. But we do have this sense then that as we go from the roadside, where we're dominated by the motor vehicles, so we've got gasoline contributions or motor oil, diesel fuel, to more of a community, say hundreds or a few kilometers away from the roadside, other sources start to become important. So we get meat cooking and wood burning coming into the mix as two of the dominant sources. And then I always say this as a common sense way to try to drive home the point. If you walk around a city like Toronto, there's only two things that emit visible smoke, and those are Burger King and your wood fireplace. Nothing else emits visible smoke here. And so those are still major sources of particles to the atmosphere, and they dominate ultrafine particles under certain situations as well. So meat cooking or wood burning, depending on where you are and when you are, can be very strong signals, in addition to the transportation sources that we're all traditionally used to thinking about when we talk about ultrafine particles. And then if you go far downwind, where there's days of time between the emission source and then where we make the receptor measurements, you have a hard time recognizing at least half the ultrafine particle signal anymore. And that's either because the tracers have been chemically reacted, or you've got secondary organic aerosol formation that if you give it enough time will happen in that size fraction as well. So that's sort of the picture that emerged from this study of ultrafine particle source apportionment. Now, if we look at, again, Costas' study across Los Angeles in the summer versus the winter, this is the same format of plot that I looked at previously, and we're looking now at source contributions rather than different chemical components. You're seeing, again, sort of the vehicular sources are dominating around central Los Angeles, but as you go inland, then you're getting a lot more SOA growing in. So that's showing up, I believe, especially in the summertime. It's the brown bar that I want to draw your attention to. It's labeled as other organic material, but that's where the SOA is growing in as you move downwind. A lot of the mobile sources here, that's primary mobile in the light gray. So I guess the two things to take home are that Los Angeles does seem to be dominated by mobile, which makes sense. It's lots of cars in Los Angeles. There is processing that goes on, though, and it gets more processed as it goes downwind in the summertime when the oxygen concentrations are higher. And this is just another reflection of that sort of general picture of how the atmosphere is working for ultrafine particles. I apologize for the format of this. We switched from a PC to a Mac, so it's still kind of visible, but I'll just say what I wanted to say. There's a really strong diurnal variation as well. So Costas was looking at the, in the last figure, the seasonal changes, but even the diurnal changes. So in the San Joaquin Valley, which is one of the two most heavily polluted air basins in the United States, you get this incredible burst of wood smoke at night, which really dominates the ultrafine particle emissions. If you go to any resort town where wood burning is sort of the accepted method of heating your cabin at night, you'll see the same sort of effect. You just sort of get fumigated by wood at night. And then it completely flips during the day where the atmosphere mixes more and you get more of the restaurant emissions and other things sort of coming in. So we see this very strong day-night contrast at all the sites that we looked at in the Central Valley of California, the San Joaquin Valley. Traffic is definitely there, and it's there all the time, but it only accounts for about a quarter of the ultrafine particle mass. And so these other sources are very important. We can also see a seasonal variation. Obviously, you would only have wood burning during the wintertime, not during the summertime, unless you have forest fires, which definitely happens in California a fair amount. And so we sometimes get inundated by that. Meat cooking is always present in all the seasons, and then we get a lot more of this sort of processed, we can't recognize it from a chemical mass balance source apportionment profile anymore, what it is. And it's either the secondary organic aerosol formation happening or the primary material is being processed in the condensed phase. So we've done those short-term studies. We tend to do those for weeks at a time. We did a longer-term study for a whole year where we measured ultrafine particle concentrations daily, and we were looking at how the signals would vary in time and used a different technique to try to do the chemical source apportionment for that. We used the positive matrix factorization rather than the chemical mass balance model. And we did that with the metals analysis, mostly because it's cheaper to do the metals analysis than it is to do the molecular marker analysis. And so we were here in Sacramento, right by a California Air Resources Board facility, actually. And there's major sources around us, the I-5 highway, I-80, Highway 99, there's railway, and then this is all residential and then commercial here around the facility, residential down here as well. So this is a typical urban setting in California, and we wanted to see over an entire year, how do the ultrafine particle concentrations vary and how do the source contributions vary at that location. So what we observed then was that the different components of the ultrafine particles, the organic carbon, the pyrolyzed organic carbon, the elemental carbon, sodium, magnesium, sulfur, and iron, these are months of the year spanning the 12 months that we were out, November 2009 through October 2010. We did see strong diurnal variations of that, where the organic carbon concentrations were highest in the winter time. And again, that's going to reflect the wood burning source that we observed. And so if we look at residential wood smoke, then that was highest here in the winter months at the sort of beginning and at the end of the cycle. We see a consistent regional traffic signal, which makes sense. The cars drive all year round. And so we've got this gasoline and diesel engine signal that we can see. The rail signal looked to be pretty spiky. We saw this really interesting factor here that was sort of dominant actually during the beginning of the study and then dropped off strongly in the last half of the study. It turns out that the timing of this corresponds very strongly to the adoption of clean diesel in California around the port of Oakland, where they implemented a clean diesel retrofit program. And for either coincidentally or, you know, as a causative factor then, when they implemented that clean diesel rule, this entire source of ultrafine particles just went away in our study. And there's a lot of debate about what might have happened here. Certainly those trucks emit lower concentrations of PM 0.1 as well as PM 2.5. And so it could just be straight up that the ultrafine particles are gone. But if you look at the emissions testing from those vehicles, actually, some of that ultrafine mass actually isn't gone. It just nucleates into even smaller particles, kind of like the number story that I was telling you earlier. And so our definition of PM 0.1 mass in this study was actually from 56 nanometers up to 100 nanometers, and we were blind below 56 nanometers. And so some very smart people have said that it might just be that you moved some of that particle mass down below the 56 nanometer threshold, and it might still be there. And we would expect sulfur and some other compounds that are prone to nucleation to perhaps be in that size fraction. And so this is an interesting story. Whether or not there would be as much public health benefit as you might infer from that is open to sort of debate, though, because as with many PhD studies, all the measurements weren't made at all the right times, and it's hard to go back in time and fix that. So we discovered some of the interesting questions at the end of the study, not at the beginning of the study. Okay, so if we look at the change then with vehicle technology on average, this is pre-implementation, sort of 2009, 2010, and then post-implementation, 2010 to later 2010. And this was all done, I believe this was at the port. No, this was at Sacramento, I apologize. So that old diesel fraction here in the dark color just completely went away from the source apportionment. The concentrations didn't change that much. Well, I guess they did, but this one's hard to know because just how the seasons worked out. This time period had much more residential wood burning than this time period did. And we understand that seasonal signal. That wasn't the interesting part. The interesting part was why that old diesel signal went back. And will it return? There's another hypothesis that says when you put out these new trucks with the new emissions control system, the emissions control system kind of acts like a sponge at first. So for the first 10,000 or 20,000 or 30,000 miles, there will be adsorption of the sulfur compounds irreversibly onto that emissions control technology. And then after that, you kind of fill the sponge up. You can't adsorb onto it anymore, and stuff just starts coming out the tailpipe again. And so we're quite curious about whether or not this would come back, say now, if we measure again, whether that profile would still be there. Okay, so on to toxicology, and I'm running long here, so I might breeze through this fairly quickly. The key hypothesis here is oxidative stress for what causes the PM health effects, both in the PM 2.5 size fraction and the ultrafine size fraction. And so Kostas has done a lot of work then looking at the apparent oxidative stress of particles that he collects at different seasons and different locations in Los Angeles, and looking at whether there's seasonal differences or whether there's differences in time of day or location as well. So what he observes then, if he looks at the apparent oxidative capacity of ultrafine particles, is that there's much higher oxidative capacity in the summertime than there is in the wintertime. Sort of going along with this hypothesis that it's the processing, the atmospheric processing of the particles that makes them especially toxic. So you can do that either in absolute concentrations, micrograms per cubic meter, or you can do it per unit, per microgram of PM. it looks more toxic either way you look at it. They attempted then to relate this toxicity, this oxidative stress, to the different sources at Long Beach, Central Los Angeles, and Riverside. And then what they found at the downwind locations is that it's the water-soluble organic carbon that's playing the dominant role in explaining that toxicity. So Kostis would argue then that the ultrafine particle toxicity at Riverside, the downwind source, is largely driven by the water-soluble organic carbon, the amount of processed organic aerosol in the ultrafine size fraction at those locations. He also sees evidence of this if he looks at the diurnal signal. So he's made measurements throughout the day focusing on the morning rush hour or the afternoon sort of photochemical peak. And if he compares those two samples, what he sees is that he's, obviously seeing more evidence of ultrafine particle generation in those afternoon samples. But he's also then looking at the apparent toxicity, the oxidative capacity of those ultrafine particles. And again, what he's seeing is that either per unit mass or per meter cubed of air, the afternoon samples, the more photochemically processed samples, are the ones that have the apparent higher toxicity. And so that suggests to him then that they're bad actors. More evidence coming out of photochemical chambers. And so if you take fresh emissions from a traffic tunnel in California and you look at their apparent toxicity, their ability to generate oxidative stress, then you get one sort of result. If you dilute the samples then in the ambient atmosphere, you can tell how much dilution has happened just by looking at the CO concentrations as a sort of a non-volatile, non-reactive tracer for vehicle emissions. You get a much lower oxidative stress, but if you take those particles then and age them photochemically, you can sort of turn them back into the high oxidative stress levels that we observed even with the fresh emissions here. So the evidence that, again, suggesting that photochemical reaction happens. Okay, so on to epidemiology. That's all results from toxicology, but you can't really say anything definitive without epidemiology as well. And it's been really confusing with epidemiology, and actually kind of ironically so, because when we developed the PM 2.5 standards, it was the epidemiologists that found the association first, and the toxicologists struggled for years and years to explain it. They said it's not plausible, it's not plausible, and finally we got plausibility. It's just completely the opposite for ultrafine particles, where it's the toxicologists waving their hands saying, hey, stuff is really, really bad, and the epidemiologists can't see it. Well, maybe they can't see it because we've been looking at number instead of PM 0.1, or we haven't done the exposure characterization well. And again, the exposure characterization is hard because the spatial gradients are much, much sharper for ultrafine particles than they are for PM 2.5. So this is just a slice through California's atmosphere going from north to south, looking at the PM 2.5 concentration versus the ultrafine particle concentration. And you definitely do have spatial gradients in PM 2.5, but you have much sharper spatial gradients in PM 0.1. And that is consistent with modeling and with measurements. And so your central site monitor, again, it's not going to work very well. You might have got away with it for epidemiology in PM 2.5, but you can't characterize the population exposure well enough with one measurement in Toronto because there's so much spatial variability. So here we come to modeling then. And the idea was, can we use a regional chemical transport model, since we have measured all these source profiles and we know how to put them into models, would that model have any skill in predicting a population exposure to ultrafine particles? Not number, but PM 0.1 mass. And those are, again, very, very different questions because number is dynamic and it's hard to model nucleation and evaporation of that stuff. PM 0.1 is much more stable. And so here's a modeling grid for California. I'm just showing the population density here. This is Los Angeles, this is San Francisco, Sacramento, Davis, where I live. And then we're trying to model at fairly high spatial resolution, 4 kilometers in this study, soon to be 1 kilometer when we repeat it, for a 10-year period. And we want to build up a data set then of exposure, and would you be able to see relationships between PM 0.1 and health effects in an epi study? So there's a lot that goes into this, and I put all these slides in, and I'm going to have to jump right over them, but I'll say the words if not point out the trends. Just the problems in predicting the wind fields is a huge headache, especially where you have mountain valley systems. The MET models that use to predict the wind fields so that you can do the chemical calculations, they tend to be biased towards high wind speeds.
So they were developed to model hurricanes, so you can't really blame them for it. We're trying to model a stagnation event instead of a hurricane, but they tend to over-predict those stagnation events. And if you can't get the stagnation events right, then nothing else matters in a calculation like this. If you can't predict how the air is stagnant, then everything else just blows away, and that's it. So more than anything else, you have to do bias corrections for this. And there's whole papers written on how to do this, and I won't go into it now, but just to point out that that's a big issue. When we try to do the comparisons between the measurements and the model predictions, we actually see fairly decent agreement. So the dots are the measurements here. This is daily elemental carbon over a multi-year period. This is just 7 years of the 10-year data set at Sacramento, Fresno, Bakersfield, Los Angeles, and Riverside. The red lines and the blue lines are both model predictions, but the blue lines are if you took literally the grid cell where that monitor was located, and the red lines are if you allow yourself to hunt around the monitor a little bit, say a few grid cells in any given direction. And why that matters, you know, if you don't predict the wind exactly right, then you're going to completely mess this up as well. And so, you know, the red lines agree with the measurements much better than the blue lines do, especially at some of the sites where you have relatively small urban footprints like Fresno. And so, you know, these are all issues that have to be weighed as you try to do this type of estimate for exposure. That was elemental carbon. This is the same thing for organic compounds. We were using CMAX SOA model in this, and there's a lot said now about secondary organic aerosol modeling and how you have to have semi-volatile primary compounds and have it all come back. You know, we had none of that here. This was more of a traditional SOA model. You know, you look at the performance in Los Angeles or Bakersfield or Fresno, we didn't do that bad. You know, and so that you can infer what you want out of that message. Now, the take-home that I should point out, though, is all these peaks happen in the wintertime when you're wood smoke dominated, and all the low points are the summertime. So, yeah, maybe there is some evidence in Los Angeles that we're not, you know, predicting as high as we could in some of these summer events. But and certainly at Riverside, there's evidence of that. There's a lot of things happening at Riverside. There's a big ag sort of source directly upwind of Riverside, and there could be missing emissions. There's a lot of things happening there. So, you know, the fact that we can do this in a lot of places in California without completely sort of overturning the model for primary organic aerosol and secondary organic aerosol, I think has meaning. But again, I leave it to your interpretation. So that's all for PM 2.5. Here again, more PM 2.5 comparisons. We try to evaluate the model for PM 2.5 because if you can't get that right, then you probably aren't going to get PM 0.1 right. So you always start with the stuff you think you can do before you push on to the sort of more advanced stuff. And so we're doing pretty well doing the comparisons between the predicted versus the observed. This again is, it's labeled as PM 2.5. I want to say this is PM 0.1, but maybe that's wrong. The bottom line is that the model we think has skill for lots of different things like elemental carbon, potassium, chromium, zinc, iron. If you look at all the different sites where measurements are available and we do the comparison, if it's green and says 0, that's perfect agreement. And if it's red and a number very different from 0, that's very bad agreement. And what we take out of this type of evaluation is that the model does work well for some things, but it doesn't work well for everything. Now, sodium, the thing that worked worse than this, we didn't have sea salt emissions in this particular model run, so I don't expect it to work for sodium. But for other things, it is working quite well. And what we are trying to characterize this as is that use the model for what it's good for and don't use it for things that it's not good for. Rather than trying to use these measurements to correct the model predictions, we're just trying to use the model straight up, but only the features of the model that we think have skill. Why would it do poorly in some of these locations? Well, maybe we don't have the emissions right. Or maybe we can't predict the meteorology there quite right. And so we just want to make people aware of that as we try to share this data set with epidemiology. We can also compare the sources that are predicted from the model to the receptor measurements, either with the chemical mass balance model or the PMF model. So all the emissions models now are what we call instrumented, or they use tracers, or however you want to call it. We keep track of the sources throughout the model calculation, both primary and secondary sources. And so in this 10-year data set, we know the field of mobile emissions, PM 0.1, and we can compare that to measurements where measurements are available. So this is PM 0.1 elemental carbon at Sacramento, Modesto, and Bakersfield, comparing the contributions from mobile, wood smoke, and meat cooking between the chemical mass balance receptor-based one, where we try to make measurements, analyze those filters, and recognize chemical fingerprints and say how much of a certain source was there, versus the emissions-based model, which is in the red here, so comparing the two. And by and large, they agree quite well. So all that is another boost in confidence that the model has some skill. Not perfect skill like I showed on the last slide. There's some red there, but it has some skill. And so for the things where it's doing well, perhaps it would be useful for epidemiology. So we start to generate these exposure fields then. This is an exposure field for ultrafine particle elemental carbon across California over a 7 or a 9 year period. You can see the hot spots lighting up in Los Angeles, Bakersfield, Fresno, San Francisco, Sacramento. All the major urban centers have that. And we think that we can then think about where the people live relative to those exposures and think about whether or not those people are being challenged, is their health being challenged because of that exposure. So we can not only do it for ultrafine particle elemental carbon, we've got PM 0.1 mass, we've also got all the different sources. So diesel engines, gasoline engines, dust, wood burning, meat cooking, high sulfur fuel shipping. We actually took all 900 sources in the emissions inventory and we tracked them all separately. Thinking that it never been done before, so why not? And I like supercomputing as much as the next guy, so why not? So we chewed away on this for the better part of 9 months or something like that on a very large computer cluster, for 10 years worth of data basically, and then saw what we got. So this is all aggregated then into the top 8, 7 or 8 sources, let's say. And then this is just the regional source apportionment of ultrafine particle EC as well. So all of this then we're freely available. It's up on the website, and we've worked directly with some epidemiologists. Some epidemiologists are just picking it up and trying it. The study that I'll talk about today was done with Bart Ostro. He was the chief epidemiologist for California before he retired. And this is working with a cohort called the California Teachers Study. And so this is a study of tens of thousands of teachers in California over multiple years and looking at their risk of dying relative to their exposure. So they're looking at their hazard ratio. So I'm not the statistical wizard, at least when it comes to this stuff. And so this is a cost proportional hazard model with time varying exposure, similar to what Bart had done based on exposure estimates for PM 2.5 based on central site monitors. And then we know where the people lived, and when someone dies, then we look at their cumulative exposure and we compare that to the population that didn't die. And then we're, of course, trying to control the risk factors like body mass index, smoking, and diet, and everything that we can. So the original study that Bart did using central site monitors for PM 2.5 risk found a hazard ratio of 1.2. And if we repeat that same exercise for PM 2.5 with our model exposure, not measurement, but model exposure, we get almost the same answer. So we get 1.18 as opposed to 1.2. And so that is a good confidence booster again. Remember, you're supposed to be able to do the things that you think you can do before you try to do something new. So this sure should work for PM 2.5 before we try to apply it for ultrafine particles, and in fact it did. If we move on to then the ultrafine particles, and we look at those hazard ratios, I'm not just listing mass here like we had in the last table, but I'm listing the different fractions of the mass or the different sources. We see some interesting things. So first off, PM 0.1 mass by itself looks like it's positively associated with that excess risk of dying in this cohort. You can see a pretty strong association with things like elemental carbon. You can also see a very strong association with the secondary organic aerosol. So why is that exciting? Because the toxicology that Kostis had done with measurements seemed to point to the secondary organic aerosol in the ultrafine fraction as being more toxic than everything else. And that's in complete agreement with this prediction for secondary organic aerosol as well in an epi study using completely independent methods. And so where you get agreement between toxicology and epidemiology, you start to think that maybe something's real here. Now, the caveat with this is that one epi study doesn't mean anything. You need 5, 10 epi studies before you really draw strong conclusions. But if 2 or 3 more epi studies match this, you may well see an ultrafine particle standard at some point. It's a real possibility that something could happen like that if this is matched with further studies. Now, do I think further studies are going to agree with it? I don't know. I'm interested to find out. You all should go out and run one. That'd be awesome to see if it really matches this, because I think it is a compelling question that comes out of this work. One of the other interesting things that came out is that wood smoke wasn't strongly correlated, and in fact was anti-correlated with the apparent hazard ratio. And so I don't have an interpretation for what that is. It's one of the largest sources that we have of ultrafine particles, and yet it's not. The traffic sources all came up positively associated, but wood smoke not. And so I find that also quite interesting. Meat cooking was positively associated. So as with all research, many questions are asked as well as answers provided as you go through these steps. Okay, so I'm out of time. So what conclusions can we come up with? Ultrafine particles, there's lots of different metrics that you could use to characterize them. Number is the traditional one, but I'm making a pitch for numbers not the be-all and end-all. I think number actually is interesting because it tests a completely different set of hypotheses, and those are worthwhile things to look at. And those hypotheses centered around the 20 to 40 nanometer particles that are very dynamic, that are prone to nucleating and evaporating in the atmosphere. And I think we should be doing health studies of those particles. What we observed, though, and I was involved in the HEI review of this, there's not strong evidence so far in the number of studies that have been done for an effect from those particles. What I'm pivoting towards then is PM 0.1 as a metric of ultrafine particles, which is highly correlated with surface area, in which we can do a better job of estimating exposure assessment to. We can do source apportionment with it, with receptor models. We can predict it with grid models. We can measure the chemistry. We can watch how it evolves in the atmosphere. It appears to get more toxic through the toxicology measurements that are made in the atmosphere with aging. When we predict with grid models and do exposure assessments over whole years or multiple years, it appears to be correlated with health effects. And it appears maybe that the atmospherically processed portion of it is the most correlated with health effects, which matches the toxicology. So that starts to draw together a compelling picture. Now, there's future work that, of course, has to happen. And one of the future questions is this just the PM 2.5 effect recycled? Whereas maybe if we would have been measuring PM 0.1 this whole time, we would have found exactly the same thing that we found up until now instead of PM 2.5. This could just be because it's the tail of the PM 2.5 distribution dipping below 100 nanometers that this is really just a PM, the same thing. I guess the question that's interesting to me is which one drives it? Like if we knocked out all the particles bigger than 1 micron, would we still have the same health effects because the PM 0.1 didn't change? Or if we knock out some of that accumulation mode stuff, but we leave the PM 0.1 there, would the health effects stay the same? And I think that's relevant because part of what I think about is energy futures and what we should be controlling in California to make standards to protect public health. And that becomes very relevant. Then which sources do you go after and which chemical pathways are important as you think about those questions? And I think this all has bearing on that, and it is a really interesting question. So we'll be continuing to be continued. We're going to take another run at this in California over a 20-year period instead of a 10-year period this time, 1995 to 2015, and probably drilling down to 1 kilometer resolution and trying to do something, about the things that didn't work in the simulations this time to try to improve those exposure estimates and see if it still works. And all the data, again, will be up on the website as the current data set is, subject to the caveat that my web server crashed last week and I'm still rebuilding it. So if it's not there now, it'll be there next week, and it's publicly available. If you want to use it, by all means, grab it. I know a lot of you probably are more focused on Ontario and Toronto than California, but if you do want it, you're welcome to it. But please let me know, and I'd love to help you understand what are the strong points and the weak points of that data set to help you best use it if you pick it up. So with that, I think I'm officially out of slides. So thanks, and I'm happy to answer any questions if there's time left.
So we are at the hour, but we do have a few questions. And then maybe if you're willing to stay afterwards, if there's a few more questions.
I can certainly hang out for a couple minutes. Yeah.
So I just came in again, sorry to hear the beginning, but just your last question there, what have you done to look at the spatial correlation between 5 and 0.1? Or similarly, SOA spatial variation versus ozone spatial variation?
Yep.
Bart? We've been using those 3, 2.5, NO2, and ozone in California. I want you to explain all these factors and sort of relate those sources.
So those are all really excellent questions, and the epidemiologists have to be involved in answering some of those questions. The study wasn't really rich in EPI funding. It was more to generate the data set, and so there wasn't time so far to go back and look at some of these questions. We know that some things are highly correlated in the atmosphere from the measurements or the model predictions. They both are highly correlated. So many of the PM components go up and down together, and that reflects common sources. And so some of these things go up and down together. We're trying to find regions where they have some differentiation so we can test these hypotheses. And that's part of the motivation for going back and doing it again at 1 kilometer resolution and really trying to drill down on some of these things. So
that's why the last figure you showed has different risks by different points because they have their own.
Yes, but there still is.
Gases like that.
Right.
What explaining itself.
Right, and so PM 2.5 versus PM 0.1, those things are correlated, as they would need to be for this to be real, I think. So the question again that I come back to is which one drives the health effect, though?
That's a good point, and that's really the question. Can you find somewhere where they don't co-vary or design the figure so they don't co-vary?
Probably didn't give me $1 million, but close. But yes, that is the big important question. Can you find areas where they are different? And can you exploit that in an EPI study to test the hypothesis with statistical significance about which one drives? Other questions?
Thank you for your talk. That was really good. So the relative risk that you showed, that's published in our Ostro's paper?
Yes.
Okay, great. So that wasn't my question. My question, I guess that was question 1. Question 2, I don't know this literature at all, but I have heard that there's some new literature on coarse PM being associated with adverse health effects as well. And you have, sounds like, there's some evidence now about the ultrafine being associated. I come from like the PM 2.5 camp, where,
right.
And know that literature, but I guess, do you know about the literature about the
I do know.
That was resolved, what's your sense on it?
So I believe that literature was based on measurement exposure assessments. And I think Bart was actually involved in that, ironically, as well. I don't know the details of that and how that might differentiate from what we're finding here, though. I don't know how prevalent that is in the literature now. I know that EPA has done several core studies, but I haven't kept up on the outcome of that. What I would point out is that if you look at the major loss mechanism for these ultrafine particles, one of them is coagulation. And what do they coagulate with? With coarse particles. And so you've got a direct pipeline from the ultrafine mode to the coarse mode, removing these particles from the ultrafine size fraction. And are they still toxic when they get to the coarse mode is a good question. I always think of ultrafine as being particularly dangerous because it's basically the mass you can shove across a cell membrane is the PM 0.1 mass. You're not going to shove a 1 or 2 micron particle across a cell membrane, but you'll shove a 75 nanometer particle across a cell membrane. And what is it carrying with it when it does that? Whether a coarse particle then can take those up and then they deposit somewhere else in the respiratory system and they can then mobilize. These are all interesting questions, but it's more of a hypothesis than anything. Toxicology is going to jump all over me, maybe.
So are the size distributions in Riverside generally larger than those in central LA? Because you've got more secondary.
The secondary push lands in the accumulation mode. So it will push material up into that 600 to 800 nanometer, but it doesn't really push it beyond that. And I was wondering just with Arthur this morning, why is that? The conventional wisdom is that the deposition of particles sort of strips them out of the atmosphere quickly after you get too much above that, and so it's loss that sort of trims off that big stuff. But I'm not sure that that's the only reason. For some reason, though, the secondary processing tends to move things into the accumulation mode.
I was thinking, just following up on Jeff's question, if the size distribution is somewhat different, like more ultrafine in central LA versus Riverside, could you approach the epidemiological?
Well, that's exactly what we're trying to do, but so far we haven't been able to get enough separation with our initial look, and we're hoping that at 1 kilometer resolution and more attention to that hypothesis going into it, that we will be able to find zones where we can do that. You need a lot of people living someplace where they're correlated and a lot of people living someplace where they're not correlated in order to test it, and we just haven't figured out where exactly that is yet. all the cities kind of look the same. There's no major point sources in California. The ports are the closest thing that we have to what acts like a point source. But other than that, there's not, you know, we're all driving cars, we all eat at Burger King, we all need to heat our houses.
Great. Just to have this slide out, so you mentioned the high seasonality to the smoke.
Yes.
I'm just wondering, and there's the high seasonality to the SOA as well. So I'm just wondering, I have no idea how it would be possible to adjust for this. But do you think there is any sense that these data were adjusted, that's a winter-summer effect there, not a wood smoke versus SOA?
I don't know how they stratify the data when they do the EPI. And that'd be a great question for Bart.
Okay. I didn't know the answer either. I just can't see how they would, because the wood smoke jumps out of winter, so we don't have. Right. Maybe there's enough forest fires that you can test in the summer, but.
No, there's not.
Yeah.
It really isn't. I mean, if you look at the exposure to forest fires, they're sensational. They make the news. It looks, you know, very, very terrible for a week, but it's 1 week of the year. If you look at what you're really exposed to, it's what somebody drives down the road. It's not the forest fire, even though it looks terrible for a week.
This is a long-term cold warning that they would have been following features for many years, and they would have just generated average annual surfaces for each of these. Probably not seasonally based surfaces. They would be like you could postulate that with smoke, but it's really winter time saying that it has greater cooler, maybe having a different time activity than winter versus
Okay, well, with that, thank you to join me and thank Mike for a wonderful presentation.
Thank you.